folks join in. Thank you. We are recording this, so happily it'll be available later for anyone who'd like to watch it. And we'll provide the slides at the end as well. So don't worry about taking furious notes because you will be provided with a PDF as well. I'm Andy Pease. I'm an architect and lead accredited professional with Inbalance Green Consulting. I'm here presenting today with Tatiana Soglin, a lead Green Associate, also with Inbalance Green Consulting, and we are talking today about addressing the energy water nexus. It's part of our net carbon, zero net carbon design series, as presented through 3C Ren. And then we also have Itzel Torres with 3C Ren, and she'll be a resource as we're going through. So I'm going to start with a few comments about the 3C Ren, that's the Tri-County Regional Energy Network. It's why we're able to be here today to make this presentation, and we're a proud partner to work with them on their programs. 3C Ren is the 3 counties working together to be able to provide programs that are specific to our area using ratepayer dollars that would otherwise be having PG&E and Edison spending on kind of some big programs, but our counties got together and said, hey, there's some gaps. So let's figure out how we can serve our local professionals. And there are 3 main programs at this time. One is the Energy Code Connect, and it's trainings for folks who are into the industry. It could be architects and building officials and builders and engineers, and it's specific about the energy code as well as the California Green Building Code. And so we provide a lot of classes, but there's also an energy code coach. We'll talk a little bit about that at the end, but it's a free service. It's available to anyone who has a question about either the energy code or Cal Green, and there's a hotline, and there's an online form. And again, Inbalance is proud to be a contracted provider for that service. So the certified energy analysts in our office, Grant Murphy and Jennifer Rennick and some others of our team, will respond to those. There's building performance training, and that's how this class today is provided for current and prospective building professionals. It's a lot of sometimes very technical, but also how to sales and marketing for folks who are getting into this industry. And then finally, a home energy savings program, which is more direct install. So we're going to jump into this class. It's the 3rd in a series of 5. And so just to make sure we get to cover some of the logistics of what we're doing here today, the California licensure now requires 5 units of continuing education for zero net carbon design. And so we partnered with 3C Ren and their building performance training to craft a course with all 5 hours of to address that learning unit. It also qualifies for AIA continuing education, so it's a both. So if you registered you want your AIA units and you plugged in your number, 3C Ren will report it directly. And for the California, it's self-reporting, but you probably want some kind of a certificate. Today's class is worth 1 learning unit, but we're kind of waiting to the end of the whole series and figuring we'll just track the attendance at the end so that you'll get your 2 units or all 5 units or whatever. So Itzel's in charge of that. So you should be seeing AIA learning units and the certificate at the end of the whole series. But if you need something sooner, we'll have Itzel's contact information for you. So here's our learning objectives for today. It's really all about zero net carbon. The first class where we really were talking about the fuel mix in California and the grid and how that's making some decisions, influencing decisions for California's energy code. We're talking about operational carbon versus embodied carbon. So what is the carbon needed to run a building versus build a building in the first place and make those materials? The energy water nexus isn't often a part of our energy conversation. I'm going to make the argument today that it should be, and is really powerful that way. And then as we continue on, we'll be talking about ways to evaluate and understand embodied carbon, and then it'll wrap up with regenerative design. So a little bit more of the what can we look forward to, what's the big picture on all of this. So this is the schedule. We've done the 2 already. You can watch those online. Today is energy water. And then August 31st and September 19th are the next 2 classes. And you do need to register for each one individually. So if you have questions along the way, Tatiana and I are going to be trading back and forth with the content, but feel free to add in the chat. We can, we plan to wrap up by 1 o'clock, but still be available for Q&A at the end. But if you have something pressing, just go ahead and let us know. So there's about 30 folks on the call, so we'll be able to get to those questions as we go. So today we're talking about energy water nexus itself, and then how do we address it in terms of the efficiency, capture and reuse, additional considerations, and some case studies. So what is it? Why, when we talk about water, are we also talking about energy? So here's a water body, and at some point that water body has to make its way from this source, wherever this is. This is up in Oregon, but could be Northern California or wherever, and make its way to us. So as we think about how does water use energy, it's kind of 2 main categories. First, there's the collect the water and transport it and treat it, right? So it's at a reservoir or a snow belt, or however we're getting it. There's some pumping that gets it up and over hills, gets it to our water treatment plant, treats the water, more pumps, gets it into our businesses and homes. We wash our hands with it. Then it goes down the drain, and then it goes to a wastewater treatment plant of some kind. And there we go. So that was water, right? So all of those stages require some use of energy. So our main strategy is to, reduce the amount of water that we're using in the first place, and to try to utilize water that's local and lower energy. And then on top of that is that we use a lot of energy to heat our water. And so again, if we, want to shower or clean things, great, let's heat our water. But again, when we can reduce our water use, we're saving energy. And then we're also going to talk about low carbon or lower carbon for water heating. So there's some good news on the waterfront, is that generally we're becoming more efficient. So even though our population is increasing, our water use is really stabilized. So this is a chart that's showing California water use from 1960 all the way to 2015. And the shaded gray area is the increase in population. And then the orange bar is showing urban water use. So kind of low, kind of went up a little bit, but then some 1990s water regulations. So that starts to level off and even creep down. So that's total water use, not per capita. And then the green is agriculture, and then the blue line is the total use. And so you can see even agriculture, even though we're very productive in what we grow, we're actually getting more and more efficient with the water that we're using. And so we see that 20% of California's electricity and over 30% of its natural gas usage goes to water. And it depends on how we're getting the water. I love this chart. It's talking about the water supply and its energy intensity. So it's kilowatt hours per acre foot of water. And you can see, like, way up at the top, the most energy intensive to procure water as a source is desalination of seawater. It just takes a ton of energy. And that's with today's technologies, right? So we understand that there might be other things that are going to happen in the future, but this one is about using a lot of energy and other potential impacts from seawater. Then the next one is the State Water Project. And that is such a big bar because it totally depends on where you are, right? So if you're kind of up close to the initial source in Northern California, it doesn't take that much energy. That's kind of just like a regular surface water situation. But if you're using it all the way down in Southern California, then again, that's a lot of mountains to go up and down in terms of pumping that water in the first place. Colorado River, similar. So then we go to recycled water to potable levels. So there's a lot of recycled water available for irrigation, but as we try to get to potable levels, it's a lot of treatment. And then, captured stormwater, relatively low energy, groundwater, relatively low. We're just kind of pumping it out of the ground. Recycled water to non-potable level, well, we have to do a certain amount of treatment anyway. So just to get it to that recycled water stage, not very challenging. And local surface water, if you're just kind of getting it from the local creeks, that's pretty low energy intensity in general. And so that's just kind of getting the water. And then we have the whole thing about hot water use. And it really is a lot of the residential use for showers, as you would imagine. And this is kind of a couple different charts just to show how we're using our hot water. And so the first one is showing like all homes, water heating is just under 20% of the energy use there. And it's kind of stable for the different units, but as you get to apartment buildings, you see that's a bigger progression. So we have a higher density of people, lower energy needed for space heating, and just there's more people, so more energy used for hot water. Same kind of a different way to present it on the bottom chart is we're showing space heating and air conditioning. Doesn't really matter how many people there are, but for water heating, it's a direct correlation. How many people are there? And if you factor in teenagers, it would just, climb from there. Yes, remember those days. So this chart is kind of revealing in that way because, again, this is about the energy use, not the volume of water. And so we're seeing water operations take a certain amount for conveyance and groundwater pumping. But that energy terms, residential water end use is like, 42%. And then non-residential, I mean, that could be any kind of industrial, restaurant use, food processing, all medical, all those things that might need in continuing water uses. But when we think about agriculture, we think, well, gosh, it's agriculture that's the big water user. That is true, but agriculture in terms of energy use is really small. So that's kind of the 2% for agriculture processing that might need some hot water. And then we have groundwater pumping. So it's a very low energy use because you just kind of pump up the water and irrigate with it, right? But a shower, that's 14%. So that gets back into the world of why this matters for architects to be so involved with water savings when it comes to zero net carbon design. And then this study was kind of the aha moment for me because what it showed was there was a study at UC Davis Center for Water Energy Efficiency. And after the 2015 drought, they did a study of the energy efficiency programs that were offered by the investor-owned utilities, IOUs, so the PG&E and the Edison, and they were like appliances and HVAC and lighting and refrigeration, all those things, and they saved, so many gigawatt hours of energy. But then the programs that were just targeting reduced water, so shower heads, faucets, things that were going to save water, actually saved more electricity. So they saved the water and they saved more electricity than all those other programs that the IOUs were presenting. So you go, okay, yeah, so energy, water, nexus, that is kind of what we're about. And so we jump into water efficiency, and we'll talk about indoor water and outdoor water, and then get into some of that capture and reuse. And kind of the opening comment, as you are thinking about your own projects and how to utilize this information, is that there's a certain amount, there's just some certain analysis that you can kind of project how much water you're going to use so that you are using the right strategies that are going to be the most effective. And super early on, I think it was our first LEED certified project, Niner Wine Estates, back in 2008. And so, you know, big winery, and they were wanting to get LEED silver. So we did this water efficient, you know, sinks and toilets and showers and all those things. And we're saving like 30% by having this lower energy or lower water use. And we thought, well, that's pretty good, 30%, you know, it's 50,000 gallons. But then we did the calculation for the irrigation and made some, you know, different plant choices and more drip and that type of thing. And we saved like 3 million gallons, right? So the order of magnitude was just crazy in scale in terms of what the focus is. And so in this one, when we say like a multifamily building, if the blue is the indoor and green is the outdoor water use in, you know, gallons per year, a big multifamily building might have just like hardly any landscaping, but a ton of indoor water use, all those residents showering, cooking, etc. So that's a good place to focus. Opposite is at a commercial building. I mean, you do low flow fixtures and you're saving like 2 tablespoons here and there. But, you know, if you think about like an office park that might have had like a sprawling, you know, lawn areas and you know, a bunch of colorful annuals that are kind of water intensive, then maybe irrigation would be a better focus. And then there are going to be other projects that are going to be both have some, and maybe even some compatibility in terms of the water use. So as we go through each of these strategies, I'm going to present an example of pretend project, Le Hotel ZNC. It's a very nice hotel. It's in the Central Coast somewhere. It has 120 guest rooms, let's say, and some staff and a pretty decent landscaping area. And so as we go through each strategy, we'll talk about, well, what would the real impacts be on something like that? So let's jump into indoor water use. If most of us aren't working on this kind of scale of, this is the Shanghai airport where they capture the rainwater and just celebrate it. I love this image. And with that, I'll turn it over to Tatiana.
All right, so taking a look at targeting lowered water use, the newly introduced SB 1157 will align California's indoor residential water use standard with the recommendations from the Department of Water Resources and the State Water Resources Control Board. So the current standard is set at 55 gallons per capita daily, or GPCD, which will reduce in 2025 to 47 and then 42 in 2030. So in the chart below, we have a regional breakdown for the state of California estimating urban and residential water use. We can see that the Central Coast is already at 44 GPCD for indoor water use. And the city of SLO in particular is estimated to already be at 42. So although we're already meeting that target for 2030, we can always aim to reduce that further. So one way we can do that is starting with looking at flush fixtures. So we have a brief timeline here of toilet flush rate requirements. Before 1982, toilets were using between 5 to 7 gallons per flush. Insane. And then between then and 1992, standard toilets still required at least 3.5 gallons per flush. In 1992, Congress required all toilets sold in the US to meet the standard 1.6 gallons per flush. And then in 2014, California required all toilets sold in the state to meet the standard of 1.28. So while the standard hasn't changed since then, we do have both dual flush and lower flow options that go down to 0.8 gallons per flush. And there's also alternative toilet options, including composting toilets and vacuum flush systems. Then those keep the plumbing at a negative pressure to allow flushing with minimal water use, which can go down to 0.26 gallons per flush. And toilets can also be supplied with recycled water to reduce potable water consumption. So now looking at flow fixtures, we have a similar timeline for shower head requirements. Before 1980, showerhead flow rates exceeded 5 gallons per minute. Some states then started restricting flow rates to 3.5 and 3 gallons per minute. In 1992, Congress set the standard for 2.5, and in 2018, California required all showerheads sold in the state to meet the standard of 1.8. So similar to the toilets, there's a lower flow option for shower heads. You can pretty easily find fixtures with flow rates of 1.5 or 1.25 gallons per minute. And then lavatory faucets, there's a residential limit of 1.2 and 0.5 for non-residential. And the residential faucets also have to meet the minimum of 0.8. You can also add aerators, which is a great way to reduce water usage without reducing water pressure. And we pretty regularly see 0.35 gallon per minute aerators on our non-residential projects. And and then metered faucets also reduce water as well. So an important thing to consider when thinking about flush and flow connected with energy use, like we had mentioned, is that your flow fixtures like your shower heads and faucets are going to be using heated water. So this is where the type of water heater you're using comes into play and how you're connected to the grid overall. So electric heat pump water heaters will have lower emissions than a gas water heater due to higher efficiencies. And if you don't have an electric water heater, then you need to consider where the electricity is coming from. If you have solar panels on your roof, or if you're getting your electricity from the grid, then what is the energy makeup of the grid? So looking at the chart here, we can see showing carbon savings for water. The biggest reduction does come from using less water overall. So this is just one example of the many water use calculators out there. This one is from one of our lead projects, and it's a good way to look at the baseline versus the design to see how much indoor water consumption is being reduced. So starting with the flush rates, we can see that using low flow toilets with a flush rate of 1.1 versus the baseline of 1.6, and low flow urinals with 0.125 rather than a baseline of 1. Similar story with the flow rates. First, we have the lavatory faucet with a design flow rate of 0.5, but this actually matches the baseline. So this ties back into the comment about metered faucets. So we use a non-default duration for automatic water faucets with a sensor. There's a study from Cal State Sacramento demonstrating that automatic water faucets have about a 30% reduction in water use, since, you know, it's timing how long the faucet is on versus just a person with a handle. So we're accounting for that using a 22-second duration versus the 30% default. And then the kitchen faucet has a baseline of 2.2 and a design flow rate of 1 gallon per minute. So all of this together amounts to an annual indoor water reduction of 43.23%.
So, and that reduction is in comparison to the LEED standard, which is national. So there's also the California standard, which is Cal Green. So it's something kind of in between. So in this case, if we're taking our hotel and we figure out using that kind of chart that Tatiana was just showing with how many residents and there's assumed number of toilet flushes and showers taken, et cetera, and a certain amount for the staff. And I saw in the chat that there was a question about FTE, the full-time equivalent. That just is a way to standardize. You assume a one full-time person. So if you have 2 people working 20 hours a week, that counts as one full-time equivalent of 40 hours a week. So So that helps to standardize the calculations. In this case, in our hotel, we've selected the low flow toilets and lavatories and the showers. And so we're getting this savings of 850,000 gallons a year over standard. And it's still a savings over California as well. So, but we'll keep going and see what else, where else we can get our savings. So while we're still talking about indoor water uses, we do talk about dishwashers, that they can be either for home or for restaurants. Energy Star, pretty straightforward. Interestingly, Energy Star says that that in their studies, washing by hand uses like 4 times as much water as an Energy Star dishwasher. So you can kind of picture that most Americans, the way we wash dishes. There's probably lower water use ways, but in their studies, that's what typically has. There's projects that use capture and reuse the condensate. I haven't really worked on those specifically, but we do see those in other projects. And then laundry, I do want to spend just a minute talking about laundry because there are some options there for lower water use. And so some of it's just the high efficiency equipment itself, right? So a front load Energy Star is going to use less water, sometimes, half the water of a standard. And then there's other technologies. There's this polymer bead that does a bunch of agitation, so you need less water. But the beads themselves might, there might be microplastic kind of issues. So we're not really leaning towards those right now with what we're seeing. There's some laundry equipment, it's pretty pricey, but it has like an off-the-shelf recycled water system within the equipment itself. And then there's also this strategy about using ozone in laundry water. And ozone, there's a machine that can, depending on the size of the system, it generates ozone O3. And that ozone, so there was a big study by PG&E Bay Area hotels that use ozone. And so basically what this does is that it works to do a lot of the cleaning and, taking care of the germs and that type of thing, sanitizing. And so because you can do that with the ozone, it reduces the hot water. And it works because it works best with cold water. So you don't even use hot water. You need fewer chemicals, so it shortens the drying time. You don't need bleach at all, and the linens are treated better. So you actually get kind of like all these benefits for it. So so that's what the study is showing. A couple different scales. On the left is a residential. It's just a little device that you can see there. That's the one at my house. So I've stopped using hot water at home, except in really extreme conditions where I can just turn that off and go to hot water. And then this is a commercial setting, which is a much better quality of ozone that gets injected. This is a hotel in Palo Alto that's using the ozone here. So some really good savings from that. So let's bring all that together. So let's say in our hotel, we're now using ozone. So we're eliminating the use of hot water. We're using high efficiency equipment, low flow kitchen equipment. And so with that, we're getting kind of the combined savings now is at 1 million gallons. And then plus this additional 200,000 gallons saved in hot water. So as we've seen in other ones, that's going to be huge. And then just to kind of touch on briefly, but we're not going to go into it, but of course there are other factors to consider in indoor water savings, on demand versus kind of a storage unit, central boiler versus each apartment unit having its own recirculation pumps. Like, is that going to be wasteful or is that going to be more efficient? Compact plumbing, kind of having like shown in this diagram where you have a water heater and it's right next to the shower where you're going to be using it. So you have some energy savings there. And of course, lots of insulation on the pipes themselves. All right, so let's talk about outdoor water use. This is actually from a hotel in Arroyo Grande, the Agrarian, and they did a creek restoration as well as kind of capturing stormwater into this pretty cool setting here in Tallyho Creek. So it has some educational signage as well. So when we think about irrigation, so it's not heated, but there's a lot of it is really what's going on there. So it's about half of the urban water use is for ornamental irrigation, right? So agriculture is really doing, mostly pumping groundwater or kind of having near sources. But the urban water use for the irrigation, because it's running generally through the same pipes, it's potable water. So it's doing all that work of getting from far away, treatment, et cetera. But we want landscaping, right? Because it contributes. We don't just want to let's just go to artificial turf then. Well, that's maybe counterproductive, because we want the plant life for the cool side. It reduces the heat island effect. It obviously sequesters carbon. So we want to be able to have plants that are going to grow and take in that carbon. It helps to manage the rainwater so that our creeks aren't kind of all inundated all at once. It meters that out. And so we want to be site responsive with our plant selection, kind of match the natural habitat, hydrology, the ecology of the site, kind of think about biophilic, understanding a sense of place, that we're drawn to nature. And then we irrigate when it's needed. And so apologies to any landscape architects who are on the call, because this is really the architect's hack to be able to kind of bracket a little bit of where we are. But it's important for us to understand that this is, again, just a calculation. So we have a model water efficiency landscape ordinance, MWELO or MWELO. And it's California law about how much water you're allowed to use. So similar to the energy code, in that you have an energy budget and then that's proposed. So same with water, we have a maximum applied water allowance, the MAWA, and then I don't know if we say ETWU, estimated total water use, that's your proposed water use. And so this MWELO is in Title 23 of the building code of the California codes. So all of our building codes are in Title 24. This is in Title 23, but it's also referenced in Cal Green, which is Title 24, Part 11. So it's our code. We have to comply with it. Here's a table of a landscape architect, Robert Fowler, who above and beyond color codes everything. So you go through and check your plant factor and what kind of irrigation efficiency you're using and what the square footage is. And so that's how he comes up with his proposed total water use. And then down at the bottom left here is the actual allowable maximum applied water allowance, where it's basically dependent on the location. So where in California you are and the landscape area and the other factors. And then you just kind of get this gallons allowed. So in this case, 325,000 is your allowable max. And the 240,000 is what this one was designed for, right? So it meets it. So why I think it's important is because anybody can just download this spreadsheet about what's allowable. And so you can start to bracket okay, this building, using the spreadsheets that Tatiana showed, we're going to be able to kind of do a worksheet and see how much water we're going to be calling for. And we can kind of start to bracket how much water we're going to use for irrigation and how do these things match up? Where are we going to have our highest impact? So if we again use our hotel example, if there was an old school design, this is kind of just a little snippet of that worksheet that you can download. And this one, let's just say it has a bunch of grass and there's overhead spray, and that's it's not super efficient. You have a little bit of drip irrigation for some flowers or something like that. And so this would be 500,000 gallons a year. Well, the MAWA allowance is only 300,000 gallons, right? So this wouldn't even comply anymore. And that's a design from, classic design of the 80s. So in California, you can't do that. So let's say if for our hotel, we did some lovely site responsive native and adapted species. This is actually Epic Estate Wines. Madrone Landscape did this design. It's obviously it's lovely. I think people still connect and resonate with it. But this is the kind of thing where there's zero overhead spray area here in terms of square footage. And it's just a lot of drip and low intensity kinds of project plant selections. So now we're down to 200,000 gallons a year. So now if we're using our high efficiency irrigation, and you can see we're just continuing to drop our total water use for our hotel. All right, so that's kind of the main strategy on the indoor and outdoor efficiency. So now let's go on and talk about water reuse. And so this is from Shale Oak Winery, one of their tanks that they use from it's a process. They capture the processed water that they use for cleaning tanks, and then they treat it and are able to get that back into the irrigation. So we're going to kind of walk through the least intensive to the most. So we're going to start with rainwater. Absolutely allowed within the plumbing code that you can store landscape water kind of as long as you want, or rainwater as you want to be used for landscape, right? So the tanks themselves will vary for permitting, just, you know, like in San Luis Obispo, they like them to kind of be, you know, under a certain gallon size. Otherwise you need structural engineering, and they shouldn't be like on your front lawn where everybody can see it. We might change that at some point because they, you know, they take up space and they're visible. But if you wanted to use it for indoor, you'd have to do some level of treatment, but pretty light hand on that one. So then it becomes kind of a question of how much do you need? And so in California, of course, we have a short rainy season and a long irrigation season. So I remember, like, you know, 15 years ago, people would say like, oh, let's capture rainwater. And we'd almost be like, gosh, don't even bother. You're going to spend all this money for a tank and it'll be gone empty by May. And, you know, it wasn't really seen as feasible. But now, whereas our irrigation and our plant palette evolves, then there's kind of more options there. And so, again, a relatively straightforward calculation for every inch of rain and 1,000 square foot of collection area, like a roof, you get about 620 gallons of water. And so for San Luis Obispo, for example, 19 inches of rain, 2,000 square foot roof area, you're going to get like 23,000 gallons in a year. Okay, so, you know, you might empty and refill once or twice. And so 3 or 4 gallons or 3 or 4 tanks are 5,000 gallons. Well, how big is that? Really big. So these are 5,000 gallon tanks. This is a real project by Perlu Landscapes. They do a lot of awesome rainwater collection. And for folks who otherwise maybe don't have water available, this is a great option. There's sophisticated controls and you can, you know, tuck them away. But there's also a lot of in-between options as well. So here's a 300 gallon barrel that my neighbor has. And so it just is collecting from the downspout. And then there's a hose, and she has 2 of these, and she basically does all of her hand watering, like raised planter beds, off of just these 2 tanks. But again, she's not spray irrigation on lawns, etc. A little bit bigger here, 1,200 gallon, maybe 3,000 gallon kinds of tanks that could be tucked underground. Or you could just do a rain garden. You just route the rain, the downspouts. Here, this area, this house has a downspout, and it goes to a perforated pipe underneath. And so it's kind of watering this area that's not irrigated during the year. And then on the right here is the neighbor contributing with kind of a rain chain configuration. So you're kind of celebrating the rain. So that's kind of the rainwater. It's really just about tanks and using it for irrigation. For recycled water, municipal is the easiest in that the city makes it, or the county, or whoever the entity is. We put it into purple pipe. It's usually available for parks or commercial properties or something. It's not usually going directly to individual houses because there's still a certain amount of monitoring that they want to do. But like Palo Alto, they require any building with 100 toilets or more have to be plumbed to use recycled water, municipal recycled water. So they want to both reduce the demand for potable, but also have a market for the recycled water. And then for on-site gray water, for your own personal use, there's a few, again, categories. So the simplest is if you just have a clothes washer, you can do laundry to landscape. You don't need a permit for that. You just need to collect from either your shower or your laundry. If you start to go over that, depends on if you're doing a simple system or a complex system that are going to have more requirements for permitting and engineering, et cetera. And just as a reminder, gray water is laundry and showers and bathroom sinks, aka lavatories, but not kitchen sinks or dishwashers, and of course not toilets. And for the at-home gray water, it can go to the landscape that has to be under like 2 inches of mulch. And the good thing about this is it's available all year round. So you can do commercial laundry to landscape. In this case, you probably have some more sophisticated filtration system and a storage tank in order to be able to send it to the landscape. So this is a Santa Barbara Humane, the animal facility that's currently under design with DMHA, and Wallace Group has helped to lay out a laundry to landscape system where these orange blocks are laundry rooms with laundry machines in it, and they all get routed to a series of tanks, and then they get cleaned up and go into the irrigation system. And then here's just kind of a breakdown of that. Laundry machines with ozone, so it's cold and has fewer chemicals, gets treated through different layers. You have extra, it's still connected to the city water, so you can make it up if needed, but it goes into a tank and then irrigates your plants. And then there's, on-site wastewater in terms of the actual toilet water, sink water, et cetera. And again, just depends on what you're going to do with it. There's also processed water, which typically has to get sent to the sewer, but there's more interest now in being able to treat that. And so here's Anchor Steam Brewery, which is saving 20 million gallons of water per year by their processed water. Although I've recently heard that they're going to stop making the Anchor Steam. I'm very sad about that. So if anybody has any insights onto for that one, because I hear they got bought out and closed up. So this is our final slide in terms of the of our hotel before we go into some of the case studies. But as you can see on this last one, we took them municipal water for flushing toilets. So then that took our blue for flushing toilets, plummeted that. And then laundry to landscape plus rainwater capture is putting our irrigation water, plummeting that down. So total savings is going from 3 million gallons down to 1 million gallons, which is pretty freaking significant. So that's how that's going. And so then we just think a little bit more about water and just the wonder of water, right? So we think about watershed basins of relations. I've seen it called in this great guide where we think about okay, where's our boundaries, and really is it more appropriate that we think about what watershed we share, who we share our watersheds with, and then biophilic design and connecting with nature and in terms of equity, who's getting the clean water and how. So just I think our role as designers gives us a responsibility and an opportunity to be able to think about water in these bigger kinds of ways. And there's certifications and some case studies, and I'll turn it back to Tatiana to bring it home.
So this is an overview of a few of the certifications focusing on water. LEED Zero Water recognizes buildings that achieve a potable water use balance of 0 for the past year. And that water balance is the total potable water consumed minus total alternative water used and water returned to the original source. There's also the Sustainable Sites Initiative, which is landscape performance based and is awarded to projects that enhance the local ecology. The International Living Future Institute has a water pedal as part of their program that aims to realign how people use water and redefines waste in the built environment so that water is respected as a resource. And they promote this idea of net positive water, which has to do with looking at the built environment as a regenerative force in the natural environment. So returning developed land areas to their pre-developed hydrology, water flowing within and through the site as a function of the larger watershed, healing wounded wetlands and natural waterways, as well as replenishing depleted aquifers. So our first case study here is an architecture firm in New York that specializes in green building and sustainable design. And they wanted their office building to reflect those values. So they designed a new office that achieved LEED Platinum, as well as LEED Zero Energy and Zero Water. So they put together a strong stormwater management system. Rainwater is collected from the roof and directed to a 1,500-gallon underground storage tank. And that's used to flush toilets in the building rather than using potable water. And they used porous pavers in the parking areas combined with subsurface storage and infiltration chambers that allow rainwater to be diverted and absorbed into the ground, reducing runoff from the site. So this next case study is actually an existing project. It's a courthouse building in Albuquerque, New Mexico. The original landscape design was all turf grass and impermeable paving and high water use plants. So Biohabitats did a total site redesign, and this became one of the first projects to receive certification from the Sustainable Sites Initiative. Some key features to the redesign included replacing high water use plants with drought tolerant and native alternatives, redesigning the stormwater drainage, and removing impermeable paving to increase infiltration. So they also reused the old paving material to create new landscape and stormwater management features, which also included pedestrian-friendly seating to make the landscape area more accessible. So they put a 16,000-gallon rainwater harvesting system for landscape irrigation. This, along with more efficient drip irrigation, reduced their potable water use by more than 75%. And they also included vegetated swales, rock gardens, and biofiltration beds to filter and decrease runoff from parking and plaza areas. So for a more local case study, we have the Santa Monica City Hall East building that is all electric, net zero energy, and net zero water. This project is pursuing the full living building challenge. They cut projected water and sewer demand for the building in half, in part by using foam-based composting toilets that use only 3 tablespoons of water per flush. They have a 40,000-gallon rainwater cistern beneath the building that also has a system that captures gray water and condensate from the cooling system's air handling units. And this is used for on-site irrigation. They try to use as much water as possible, and any water left unused is either infiltrated on site or sent to 2 of the adjacent buildings for their irrigation. And you can also see there's a well in the diagram, and that's used to supplement the rainwater system during drought conditions. So this last case study we have here is a residential example from Washington. and it's pursuing the Living Building Challenge as well. An interesting feature of this project is that they harvest rainwater for potable use, utilizing two 5,000-gallon tanks for storage and a jet pump that moves the water through sediment filters and a carbon block before final UV filtration. They also have a small septic system for on-site gray water treatment and a solarium planter with 2 feet of soil meant for treating and using gray water closer to the source. However, the gray water is not approved yet for indoor use. They also have composting toilets for black water treatment and a green roof. And so this is a really interesting project and was permitted without water and sewer connections entirely.
All right. And so that's wrapping up our main content here. We do want to have make sure y'all are aware in terms of the we'll get to the Q&A in a moment, but in terms of continuing education units, once again, we will provide these slides as a PDF. So you'll have Itzel's email on there, or if you have any other concerns about your learning units. If you could do the survey, that always helps us out, so we can get your good ideas and your constructive feedback, or whatever it is you want to let us know. And it goes again to it's also so it will be anonymous in that way. And then we do have 2 more in this design series. We presented this live in person for AIA San Luis Obispo and AIA Santa Barbara. And then potentially there's talk of scheduling for Ventura. And so we'll see, if you need to do a mix and match between in-person and remote, that works as well. And so those are the 2 dates, so be sure to register for those. And then very cool, on August 9th, 3C Ren offers these quarterly forums. And the next one is breaking barriers on energy-friendly permitting. So again, a different audience. And then a shameless plug, hoping that folks will take advantage of this free service for the Energy Code Coach. And with that, we thank you, and we'll stop sharing so that we can answer some questions. I know a few questions came in on the chat, so we can address those. And then as we are coming up on the 1 o'clock hour, if anybody needs to hop off, we totally understand. So let's see, Tatiana, any questions, or folks, if you're just in the room and want to turn on your camera or raise your hand, or add another question here. Let's see, I'm seeing a question about what treatment is required for rainwater to be potable and why. I think that has to do with it just sitting there and might, grow algae or something. So it's more like the case study that Tatiana was showing, where there's a kind of a charcoal filter. But I think it's, I don't think that there's a statewide standard. I think that you end up having to go through county health. If folks, this is also discussion. So if folks have other insights or worked on a project and want to share what their experience is, feel free to unmute and let us know. Let's see. Municipal recycled water is stormwater or treated sewage water. Recycled water from a municipality is typically black water. So it's toilet water, everything that's coming down the sewer. And so it's going through whatever its treatment system is. And then right now, there's a couple of, it's pretty limited permitting in terms of turning it into potable water. So like in the city of San Luis Obispo, we treat all our sewage water. It gets to a very high level. We feed some of it back into the creek, and then the rest we put into the purple pipe system. But it's only used for irrigation. In order for it to be back to that potable level, it needs to get to another higher quality. So it can either, there's a treatment, but then you can also like inject it in the ground and then it kind of takes a few months to go through its kind of a natural treating process, and then you can draw it back up as groundwater out of a well, and then send that into its own kind of drinkable, potable water systems. Let's see. Other states allow gray water from the kitchen. Why doesn't California? Any movement to change? Yes, please. Yes. Can we do more about gray water from the kitchen? I didn't mention when we were talking about gray water for laundry landscape is that you have to have a lever so that the user can switch. So if you're doing a bleach load or a diaper load or something that's really not appropriate for your landscape, that you have a little switch that will then send it to sewer. So yeah, so I don't know, there's a certain amount of a judgment call there for the users to, we trust users to kind of figure out what they can send to their garden or not. So I don't know, maybe there's some room there. Let's see, a question here. Do you know of any residential black water system case studies? Residential. I think the composting toilets is really what we're seeing more than trying to actually, so it's basically a waterless system. And then I don't know, every 6 months or a year, you've got this compost and you have to empty it manually. I was super impressed with that project that Tatiana outlined, because they allowed them to not have the actual sewer hookups, because most municipalities will still, maybe you can get away with a composting toilet, but you also have to have a sewer hookup because they don't know who the next owners are going to be, and are they going to be able to maintain that system to be healthful, right? So that's always a concern. So an actual treatment, I've seen, like ones where educational, a college building might have a living laboratory where the black water is going through series of filtrations and plantings, and pretty cool system. So I think it could be, but I don't know of a permitted one right now. If others do, feel free to chime in. Let's see, in the irrigation section, you mentioned sequestration. What does this refer to? So the sequestration is the idea of the carbon dioxide that we don't want in the that's contributing to climate change. If the plants can drink it a little faster, and then they would spit out the oxygens, or kind of our photosynthesis cycle. So the sequestration piece really refers to what are typically the natural systems that will capture that carbon. And there's either landscape plants themselves, but there's also these cool regenerative agriculture kinds of systems where the microorganisms in the soil will start to capture some of the carbon and make these super healthy ways to get back into a natural carbon cycle that the earth can keep up with. Awesome questions. We're going to stay on the line, but it is 1 o'clock, and I know everybody's trying to get through their lunch hours here. So if you got to drop off, thanks everyone. We'll linger a few more minutes. So if anybody wants to unmute and ask a specific questions, we're happy to do that. Otherwise, thanks for being here, and we'll see you at the next one. Mm-hmm. Yes, sorry, could have just said that. Okay. Itzel, I think we've done it. All right, thanks everyone. We're going to sign off. Have a good one. Bye. Bye.